After studying this module, you shall be able to know more about formation of symmetry adapted linear combination of atomic orbitals. To get more information about SALC, let us take one more example of molybdenum oxytetrachloride 2 negative, and here we will make use of only s orbital on chlorine atoms, though we can make use of p orbitals as well as d orbitals on chlorine atoms, but here for the sake of simplicity I will just take up s orbitals on each and every chlorine atom. After doing this, we will be able to verify the result of SALC so formed. Now, symmetry adapted linear combination of atomic orbitals in this module will be discussed with this help of the projection operator, and SALC so formed will be used further in construction of molecular orbital diagram. Now, before going into this, let us some brief idea into the structure of molybdenum oxytetrachloride 2 negative. Now, the various symmetry elements are given in. Now, I will explain these various symmetry operation with the help of the module. Now, let us take this molecule. Here, this blue ball represents oxygen, these white balls they represent chlorine, and this is my molybdenum atom. That is, this molecule has C4V point group. C4V point because it has C4 axis and it has sigma V's also. That is, this is along your bonds, this is also along bonds, and this is in between these bonds. That is, if I take just like this is in between bonds, this is in between bonds, and this is along the bonds. So, it has sigma V and sigma dash in themselves. So, it has C4 axis, it has sigma V, it has sigma D, and we will see the effect of various symmetry operations of C4V point groups on the s orbital on each and every chlorine atom. That is, if I say S1, S2, S3 and S4, there are 4 chlorine atoms which are labeled as shown into the figures, and I will label S1, S2, S3 according to this module, and we will now study the effect of various symmetry operations corresponding to the C4V point group only on these 4 s orbital. Now, for doing this, let us take s orbitals. I am just as told you S1, S2, S3 on chlorine 1, chlorine 2, chlorine 3, chlorine 4 respectively. The partial character table of C4V point group is also given besides this over here. That is, I am having in this character table A1 plus A2 plus B1, B2 and E. Total 5 irreducible representations are there, and we will see the effect of E, C41, C43, C2, sigma 1 V1, sigma V2, sigma D1 and sigma D2. That is, I will go on the effect of symmetry operation for this. The effect of transformation operators or symmetry operations on these s orbitals on chlorine atom, and the symmetry operations are corresponding to C4V point group. Now, let us take the various symmetry operations E, C41, C43, C2, sigma V1, sigma V2, sigma D1 and sigma 2 and try to operate these on these S1, S2, S3 and S4. Under the operation E, what happens to S1? S1 remains S1, S2 remains S2, S3 remains S3 and S4 remains S4. Now, what I do? If I give C4 rotation, C41, S1 goes to S2, S2 goes to S3, like this it is changed. Similarly, if we take C43, S1 goes to S4 and S2 goes to S1, like this all these symmetry operations are carried out, and we have seen how the S1 goes to other point groups. This the effect of transformation operators corresponding to symmetry operations of C4V point group on 4 functions S1, S2, S3, S4 is summarized in table. Let us take S1 function and see the various symmetry operations. That is, under E, S1 remains S1, C41 it goes to S2, C43 it goes to S4, C2 it goes to S3, sigma V it goes to S4, sigma V2 it goes to S2, sigma D1 it goes to S3, and sigma D2 it goes to S1. Sigma V1, sigma V2, sigma D1, sigma D2 have already been defined. So, like this we have seen that under operation E it is not shifted, under operation C4, C43, C2, sigma V1, sigma V2, sigma D1 it is shifted, and under sigma D2 it is not shifted. Similarly, we can take the function S2 and try to find out the effect of symmetry operation. S2 goes under this symmetry operation as S2, S3, S1, S4, S3, S1, S2, S4. Similarly, the S3 goes S3, S4, S2, S1, S2, S4, S1, S3. Similarly, S4 goes as shown into the row. Now, after seeing the effect and by seeing the S function which is not shifted contributes +1 and the S function which is shifted contributes 0, and by doing this we get tau S, that is reducible representation based on S orbital function as 4, 0, 0, 0, 0, 0, 1, 1. So, this is the reducible representation, and by following the standard reduction formula, tau S can be reduced as A1 plus B2 plus E irreducible representations. So, we have to now consider only these 4 irreducible representation. 2 are one dimensional A1 plus B1, another is 2 dimensional E, and we have to find out the symmetry adapted linear combinations corresponding to A1, B2 and E symmetries only, and we will make use of the projection operator corresponding to A1, B2 and E. Using these projection operators corresponding to this symmetry operation and on functions S1, S2, S3, 4, we can write down the various projection and their result. Let us evaluate A1 transform operator on S1, and after doing this, the results are summarized into the table, that is S1 is S1, S2, S4, S3, like this we are getting the results. And after getting this result, we now go for the projection operator and we will get the result as 1 upon 8 S1 plus S2 plus S4 plus S3 plus like this, and the net result will be S1 plus S2 plus S3 plus S4. So, normalized SALC is given in the equation 1 as 1 upon 2 S1 plus S2 plus S3 plus S4, that is given into the equation 1. Now, we make use of B2 OS1, that is we will go for the transformation operator corresponding to B2 on S1, or we can make use of the projection operator, and by doing this the results on this S1 is again summarized in the table. Therefore, the result of operator corresponding to B2 can be written as S1 plus S3 minus S2 minus S4, and the normalized SALC is given by equation 2, which is 1 by 2 S1 plus S2 minus S2 minus S4, which is given in equation 2. If we make use of the transformation operator corresponding to E, and let us try to operate on S1. The result for this are again given in the table, that is S1 goes as S1, S2, S4, S3, S4, S2, S3, S1 like this, and the net result which we are getting again is shown over here. And after doing the calculations, the normalized SALC corresponding to symmetry E on S1 is 1 upon under root 2 S1 minus S3, and the result is given in equation 3. Let us now take S2 function and take projection operator corresponding to A1 symmetry, B2 symmetry and E symmetries, and let us evaluate the effect of projection operator on S2 functions. Let us evaluate A1O S2, that is the transformation operators corresponding to S2. Again, the results are given in the table, that is how S2 transfers. One row shows how S2 transfers, and the last row shows A1O S2, how this is given. So, therefore, the net result of A1O S2 is nothing but is equal to S1 plus S2 plus S3 plus S4. Normalized function is 1 upon 2 S1 plus S2 plus S3 plus S4. This is the same result as we have obtained in equation. Now, if we make use of B2 OS2, let us take the transformation operator corresponding to B2 symmetry and try to evaluate the effect on S2 function. So, the result is given in this row against S2, S2, S3, S1, S4, S3, S1, S2 and S4, and B2O S2 is given as shown over here. And therefore, after these calculations, we find the net result is given in equation 4, that is normalized SALC is 1 upon 2 S2 plus S4 minus S3 minus S1. Now, if we make use of EOS2, that is the transformation operator corresponding to E and how it operates on S2, that is we will take up the symmetry operations corresponding to various transformation operators and we will go for the symmetry E. Now, here again I will take the function S2. S2 goes as S2, S3, S1, S4, S3, S1, S2 and S4, and the results are summarized again in equation 5, that is we are getting here 1 upon under root 2 S2 minus S4. Let us now take S3 function and take projection operators corresponding to again A1, B2 and E symmetry. Let us evaluate the effect of these projection operators on S3 functions. Now, here projection operator I am just taking the same meaning as transformation operators acting on these functions. Let us evaluate A1O S3 and what we find the result, how S3 changes, that is shown into the row against S3, and what is A1O S3 again shown in this row against this, and by just calculating the overall projection operator effect, we get the result as again S1 plus S2 plus S3 plus S4. Normalized function is 1 upon 2 within bracket S1 plus S2 plus S3 plus S4. This is the same result as we have obtained in equation 1. If we make use of B2 and go for B2O on S3, and again we see the row against S3, that is how S3 transforms is shown over here, S3, S4, S2, S1, S2, S4, S1, S2 like this, S3 like this. And similarly I am getting the result B2O S3 as shown against this. And by just simple calculations we find the result as S3 plus S1 minus S2 minus S4, and normalized SALC is given by equation 6, 1 upon 2 within bracket S3 plus S1 minus S2 minus S4, equation 3. If we make use of the operators corresponding to E on function S3, and again the table over here shows how S3 transforms and how EOS3 is there. And again by simple calculation it comes out to be 1 upon under root 2 S3 minus S1, that is equation 7. Let us now take S4 functions and make use of the projection operators corresponding to B1, B2, E, and again evaluate A1O S4, B2O S4, EO S4, and these results again are summarized into the tables below, and after recalculating or just by calculation it shows that one of the SALs is the same S1 plus S2 plus S3 plus S4 as given in equation 1. Therefore, normalized function is 1 upon 2 S1 plus S2 plus S3 plus S4. Now, if we make use of B2 O S4 and we again find out how S4 transforms, that is given in the row against S4, that is S4, S1, S3, S2, S1, S3, S4, S2 like this, and also in the row against B2O S4 I am having how S4 transforms, and again just by completing the full projection operator we get the result as S4 plus S2 minus S3 minus S1, or the normalized SALC is given by equation S4 plus S2 minus S3 minus S1. Finally, if you make use of E operating on S4, again here we look up the table and see how S4 transforms. S4 goes S4, S1, S3, S2, S1, S3, S4, S2 like this, and similarly EOS4 is transforms as given into the row, last row of this table. And just completing the whole procedure, the normalized SALC is given by equation 9, 1 upon under root 2 S4 minus S2. So, SALC given by equation 1, 2, 3, equation 5 are different. All others are same except with minus sign. That is, these are 1 upon 2 S1 plus S2 plus S3 plus S4. Equation 1 corresponds to A1 symmetry. 1 upon 2 S1 plus S2 minus S4. Equation 2 corresponds to B2 symmetry. 1 upon under root 2 S1 minus S3, equation 3 corresponds to E symmetry. Now 1 upon 2 under root 2 S4 minus S2, equation 9 corresponds to E symmetry. Now you will say how you have gotten these results. Now you can check the orthogonality of these SALC with all the other SALC which have been developed. And for finding the second SALC corresponding to E, I have to take differences of the various SALC obtained above. In this manner, I have taken MoCl4 molecule in which on each chlorine I have taken s orbitals as the basis function. Now, what we have learned in this model? We have learned more about symmetry adapted linear combination, and also we have taken the example of molybdenum oxytetrachloride 2 negative, and in this molecule we have used s orbital on each chlorine atom as the basis for developing SALC. And why these are important? These later on you will see this s orbital overlapping is very important in construction of molecular orbitals. Now also verification of SALC is so obtained. I have carried out for few verifications. You can verify the 4 results which have been given to you in these equations, that is the SALC corresponding to these equations are really the correct SALC for molybdenum oxytetrachloride 2 negative using s orbital on each chlorine atom as the basis.